All right, guys, in this video, I mean the first session at least, we are going to solve a few questions from 3.3. It is about the inverse of a matrix. Okay, if you had a look at this section of this chapter, it starts with the definition of the inverse of a matrix, right? And after that, there's a formula to find how to find the inverse of a matrix, which is 2 by 2, right? The 2 by 2 matrix formula is that we are going to, what is it, use to solve a few questions. And after that, we will talk about the general methods, that is Gauss elimination method again, to find the inverse of any matrix. Okay, and that's all about the inverse of a matrix. And before I continue this, okay, here we have question. I can just write it here. Okay, when we just say inverse, the definition of inverse means, okay, inverse means actually multiplicative inverse, right? Multiplicative inverse. For example, when we talk about real numbers, if you're given any real number, let's say it is a, right? And for each real number, if it is not equal to 0, right? We say that it has a reciprocal if a times something is equal to 1. What is that? Actually, that is 1 over a, right? That's equal to 1. So that means that this a and 1 over a, we say that they are reciprocals of each other. So reciprocal means multiplicative inverse again. If you're given two numbers, if their product is equal to 1, then we say that these are reciprocals of each other. And that is very important, how to say, concept, especially in solving equations, right? For example, if you're given a linear equation, let's say a times x plus b is equal to 0, right? Now, how do you solve this equation? First, we need to eliminate this b from the left-hand side, because now we are trying to isolate x, right? And solving the equation means we have to produce an equivalent equation so that the answer is displayed explicitly. I can just see that, okay, x equals something. This is also equation, but I know the value of x very explicitly, right? But here, knowing the value of x is not so easy. For example, let's say instead of a, you can just write 3 times x plus 2 is equal to 0, right? Maybe for you, you say that, oh, okay, linear equation, I can see that. You can say that. But how about if I just put some more, if I put some more numbers here? And how about if we have some kind of trigonometric equation here? That means that the equation is given, so we cannot see the solution of the equation clearly. That's why by applying some algebraic rules, we call this manipulations, right? We try to produce the equivalent equation where the solution is displayed explicitly. Anyway, to do this one first, we are using some very basic properties, right? Number one is that a plus 0 is equal to a. Right? And next one is a minus a. For every number, we have also another number. Actually, a, if you subtract, is equal to 0, right? And also here, a times 1 over a, that's equal to 1. And 1 times a is equal to a. Now you may see that, oh, Mr. Cosm, these are very, very simple things. Yes, they are very simple things. But to solve every equation, we are using actually these rules. Maybe consciously or unconsciously, we are using these properties. If you do not define these properties, or if you don't have these properties, you cannot solve any equation. Okay, these are the steps that we have to go through to solve any mathematical or algebraic equations. Anyway, if you look at this equation, first I have to eliminate b. How can I do that? I can just subtract b from both sides, right? Here we have 0 minus b. And b minus b is 0. Here ax plus 0. And 0 minus b, that is minus b. And using the first property, ax plus 0, that's just equal to ax. And here we have minus b, right? Also, we are just adding 0 here. This one is 0 plus negative b. Now I need to eliminate this a, so I multiply both sides by something, so we have x here. What is it? Actually, we need to find the multiplicative inverse of a, right? So here we have 1 over a times a, and here we have 1 over a. 1 over a times a, that's equal to 1. Here we have x, and here we have minus b over a, right? Actually, here we have minus b times 1 over a. Okay, let me just write it like this. Here we have minus 1 over a, not minus, 1 over a times, and here we have negative b. Now, 1 over a times a is x, so here we have 1 over a times negative b, right? And 1 over ax, again, equal to this property is just equal to x, and I can just simplify this. I can multiply this. That's equal to negative b over a. Okay. So now we got the answer. That is the solution of x. Actually, this is also another equation, right? But here I can see the value of x very clearly. X equals that thing. Okay, that's what we're looking for. And how about here? Actually, we are going to use, here, why we are going to talk about the inverse of the matrix. In matrices, finding that 1 over a, okay, that we call this multiplicative inverse of a. That is not an easy procedure, okay? So we are going to do the same thing here. So that means that, let me, okay, we're going to do the same thing here, okay? So why we need to know, learn how to find the inverse of the matrix. We know that actually we are talking about this kind of equation, right? Most of the time in linear algebra means it's all about this equation. Ax is equal to b. Now here this x is a vector, and also this b is a vector. And what is x? Let's say this x is a vector from n-dimensional space. And also here b, also it must be from the same space and dimensional space. Okay. And now here, let's say, to make this sense, also this n is n by n matrix. And when it is so, we know that actually this ax equals b. What is it? It describes a system of linear equations with n equations and n variables, right? So now we know how to actually, we studied how to solve this equation, right? That is Gauss elimination method or Gauss-Jordan elimination method, right? So for example, we need to write this in this form: A and B augmented matrix, and applying a bunch of elementary row operations, we have to reduce this to reduced row echelon form. Now I get something like this. Here we have BR, that is reduced row echelon form of A, and here we have, let's say, B prime. Okay, that is different B here. Now I need to write this equation again. Here we have r times x, right? And here we have b prime vector. This is also vector. Now we got equivalent system again. Now from here, I can see maybe I can get the solutions much faster, right? Now we have to solve the system and get the solutions of this system. All right. But now here, we are going to use another method here. Of course, under some conditions, these methods that I have just mentioned, this method number one, it can be used to solve any kind of uh, systems of linear equations. Any kind of means, like for example, maybe the number of variables is not equal to the number of equations, for example. Okay, maybe, I don't know, actually, it can be, if we are given any kind of systems of linear equation, we can use this Gauss elimination method to solve this math, to solve that system. But our second method is a little bit restricted. It's not for only, for every kind of, or any kind of systems of linear equation. Here our condition is, here this A must be n by n, okay? And this x, automatically this x is a vector from n-dimensional space, and this b is also a vector from n-dimensional space, right? So at the time, if I write this equation, okay, so that's equal to b. Now I wonder, okay, is there any possible, is it possible to find another matrix so that when I multiply both from the left hand side, let's say this b times a, here we have x. and also multiply b by vector b. Okay, that is a general rule in math. If you're given any kind of equation, and if you just carry out the same operation to both sides of the equation, actually it does not affect the solution of the equation. That means that still that new equation will give us the solutions of the original equation. Okay, so from here I'm looking for a matrix. When I multiply a by b from left, okay, suppose that that is equal to identity matrix, and here we have vector x, and on the right hand side I have capital B and vector B. Okay, and we know that from the properties of identity matrix, if you multiply any matrix in general, here our x is vector, actually it doesn't matter because we know that also vectors are special, some kind of what is it, matrices, column matrices. So we know that the property of I times x is equal to I. Actually, that I, the function of I and 1, the same thing, okay? So that is identity element. So from here now I have x, oops, and I have x here, and on the right hand side we have matrix B and vector B. And these are just fixed things, right? We know how to evaluate this and get the answer. So that is the main idea of this section of the chapter. Okay, all we are going to do here is actually to solve this equation in this way, and after that, using this equation, um, we will generate a general rule actually to find a lot of things, because also these ideas we will use to derive some new things, new formula, new theorem, let's say, in the next section of this chapter. Okay guys, let's continue. So now let's start with the first one. Okay, so in the book we have already evaluated this in the video and also proved this, so directly I'm going to use first this formula. If you're given any 2 by 2 matrix, right, whose entries are A, B, and C, D. So now in the next chapter we'll talk about this. Now here, what is the determinant of A? Determinant of A is, I just usually use these two parallel bars. Okay, that means that is determinant of A. What is it? We just define this as A times D, A times D minus B times C, right? At the time, now I can find the inverse of this. We know that actually we just denote this by -1 in the superscript notation. Okay, so that's equal to 1 over determinant of A, and here we have another matrix. What we have here, we have uh, what is it, it is D, and just we are interchanging D and A, right? And here we have, what is it, minus B and minus C, right? So if you just check this, if you multiply these two matrices, either A times A inverse or A inverse times A, that's equal to identity matrix. Okay, that's only for 2 by 10. Now let's practice one or two questions immediately here, and after that, in the subsequent questions, we will actually practice how to get the inverse of a matrix of maybe 3 by 3 or 4 by 4 or 5 by 5. Okay, and once again, when we talk about the inverse of the matrix, we mean only square matrices. All right, so Mondol, is everything all right?
Yes, sir. Everything is good, sir.
Very good. So Mondo, how are you joining this class? With PC or laptop or iPhone or tablet or iPad or?
With my tablet, sir.
Okay. The tablet Samsung,
Kind of. Oh, Huawei.
Huawei. Good. Do you have
Hold
a
the brand
pen?
Huawei. Yes, sir.
You have a pen.
I have notebook. I have notebook with me. I don't have the pen on to draw on the tablet.
Uh, okay, good. All right. Okay. So using this one, let's just maybe one or two questions. Let's do 7, for example. It looks a bit weird. So we need to find the inverse, right? Exercise 1 to 10, find the inverse of the given matrix if it exists using theorem 3.8. Okay. What's 3.8? 3.8. Actually, that one is, this one is theorem 3.8. Okay. It says that if you're given a 2 by 2 matrix whose components are A, B, C, D, and if determinant A, that is AD minus BC, is not equal to 0, as you see, otherwise I cannot write this in the denominator, right? That's why we must have this condition. I mean, this condition must hold, otherwise it will not be, that matrix does not have an inverse. That means that not every matrix have an inverse. All right, sometimes some matrices, they don't have inverse. How do I know that? Immediately before computing its inverse, we have to evaluate its determinant. And after that, if it is 0, that means that you can just write this matrix does not have inverse. If determinant is not equal to 0, then that matrix has inverse. And also, it's actually this theorem, okay? But we will prove this theorem when we talk about determinants, not here. So in question 7, our matrix, let's say this A, whose components are negative 1.5 and negative 4.2, and here we have 0.5 and 2.4, right? So now I don't know it has inverse or not. So let's calculate its determinant. Determinant of A is equal to negative 1.5 times 2.4. That is negative 1.5 times 2.4 minus, but with this minus it is plus, plus 0.5 times 4.2. And which is equal to, what is minus 1.5 times 2.4? Minus 1 times 2.4, it is 2.4, and half of it is 1.2. That is minus 3.6. Plus, and how about 0.5 times 4.2? It is half of this. That is 2.1, which is equal to minus 1.5, right? Or just simply it is minus 3 over 2. Okay. So after that, then, since it's not equal to 0, now we are sure that this matrix has inverse. So the inverse of A is equal to 1 over determinant. That is 1 over this number is equal to negative 2 over 3, right? And here we have D and A. Our D is 2.4, and multiply C and B by just negative, and you don't have to change your places. So here we have 4.2, and here we have minus 0.5, and here we have minus 1.5, right? Immediately, I just use the formula and get the answer. Okay. Now, if I just simplify this, bring this number inside the matrix, let's just write as a matrix here. Minus 2 over 3 times 2.4, that is 0.8 times 2, that is minus 1.6. And here 4.2 is divided by 3, that's 1.4 times 2, that is minus 2.8. And here 1 over 2, they cancel each other, that's equal to minus 1 over 3. And minus 1 over 1.5 is minus 3 over 2 times minus 2 over 3, that's equal to 1. Okay, so that is the inverse of the matrix. All right. So I think 1 is enough from this. Others, just using the formula, you can evaluate. In exercises 11 and 12, now solve the given system using the method of example 3.25. So 3.25, I think, what is it? Using the theorem, actually, we have to solve this. 3.25, let me see. Okay, good. So here, what method we have just mentioned already. So we are going to use this method now, solving that system. Okay. Let's just do only one of them here. Question 12. So first, let me just write this in the matrix form. Here we have coefficient matrix. Here we have x1 and x2. That is 1 and negative 1. In the second line, it is 2 and 1. Right? Our unknowns are x1 and x2. On the right-hand side, our constant vector is 1, 2. Right? So that means in very compact form, what we have here? Here we have A times X is equal to B. And these are vectors. So now if I know the inverse of the matrix, as you know, if you just multiply both sides by the inverse of A, now here we have X will be equal to A inverse times B. But here, make sure that actually we are multiplying from left, right, not right, because we know that in matrices, A times B is not equal to B times A in general. All right. So now here, as you see here, to answer this question, just we need to find the inverse of A first. So I know A. What is the inverse? First, we need to calculate determinant of A, because still I'm not sure actually if it's inverse or not. What is the determinant of A? That is, here we have 1, -1, 2, 1. Okay, this vertical lines, this vertical parallel lines, it means determinants, right? Brackets, it means we are talking about a matrix. So that is equal to 1 times 1, it is 1, and minus -1 times 2, it is -2. That's equal to 3, which is not equal to 0. That means this matrix has inverse. Now, what is the inverse of A? That's equal to 1 over determinant. That's equal to 3. And here we have, what is it? I need to interchange, but A and D, they are equal, so there's no change here. And multiply B and C by -1. So here we have 1, and here we have -2, and here we have 1. Or just simple, that's equal to that thing. Okay, I will multiply this a bit later. So now, what is, that's the second step. Third step is we have to evaluate, find the solution of this x. That's equal to inverse of A times vector B, right? So that's equal to, what is inverse of A? That's equal to 1 over 3 times 1, 1, -2, 1, and our vector is 1, 2. Okay, as you see here, on purpose, I didn't bring this 1 over 3 inside the matrix. I will do this a bit later. So now if you multiply this, still I have 1 over 3 here. 1 times 1, it is 1. 1 times 2, it is 3. So, 2, the sum is 3. And -2 times 1, it is -2. And 1 times 2, it is 2. So that's equal to 0. So the answer here is 1, 0, right? So if you just calculate here, what is it? 1 minus 0, that's equal to 1. 2 times 1 plus 0, that's equal to 2. Okay. Guys, I want to emphasize one thing here. The question, as you see, it's very simple. Using different methods, you can solve maybe much, much faster. Okay, now here we are practicing the method, not only solving problem. All right, we know how to solve the problem. Maybe using Gauss-Jordan method, it will be much, much faster. Even just adding 2 lines and we can get the answer. But here, we need to know the method. And that's why in midterm or quizzes, if you do not solve the problems using the method that we have studied, okay, and automatically I will not give you full score. Okay, for example, as you remember in the quiz, if I say that solve the problem using Gauss-Jordan method, you must use this method. If I'm asking to solve the system of linear equations, you must use the method that we have studied, okay? But still, a lot of students, not a lot, a few students, like especially the last two questions, they just solve this without using any methods, okay? This time, I might give you full score next time. If you do not use the methods that we have studied, then you will not get full score. All right, guys, let's have some rest, okay? I'm a little bit tired, and let's get some energy, drink some tea, and we will continue after 10 minutes, or maybe, what time is it now? Time is 10:16. Okay, guys, we will continue at 10:30. Okay, we will have 25 more minutes lesson until 10:55, and I will stop my class at 10:55. Okay,